a lot for the invitation, Mark. Thanks for the invitation, Mark. I appreciate it. All right, I'm going to start by giving you a bit of an overview and going through a few different projects. And the general theme is really about anions and cations, but also anion-triggered organization at aqueous surfaces. Oops. Is that whole thing showing up on the screen?
Yes, we can see the whole thing.
Okay, good. All right, just wanted to make sure. All right, so in general, I'm going to start out the talk talking about water surface. My area of specialty is the air-water interface. So water, ions, I'm going to talk a little bit about some new research highlights, particularly Tessina Dell's work and Liwei Yan at the very end, just one slide there. But I'm also going to spend about half the talk talking about Jen Neal, Ankur Saha, and Ka-Chun's work and a collaborative work with the Flood Lab. This is my group, and I just want to acknowledge that I don't do the work, and that I have some really great students and postdocs and undergraduates, which I really appreciate how hard they work and how interested and excited they get about science. And of course, funding. Much of the work is NSF, some is through the NSF Case Center out of San Diego, and other work that I'll show is from DOE funded from CPIM's program. So let me first talk about the tools that we use in my laboratory. And again, if I start from the top left, we do quite a lot of linear isotherms, where this is spreading a film or a partial film of a surfactant-like molecule or something that's soluble on the surface, and watching the surface tension as a function of time, but also using barriers such that we compress those films and we look at different phase transitions and different organization on that. In addition to getting the surface pressure isotherms, we also do Brewster angle microscopy. Here's an example image here on the right or in the center. And this is really just taking I think this is it's actually not a red beam in these experiments. I think it's a 543 wavelength that has just very low power. This is a low resolution image. So we're talking about the best you can do is really maybe 1 micron resolution, but it gives us a lot of information about just morphology, macroscopic morphology. So the white is more thick, essentially a thicker film. The dark blue, we have these colored blue, but the darker it is, the more water rich the surface is. And we have some artifacts in this in the sense that usually you see that the beam is a little bit brighter in the middle. But the basis of Brewster angle microscopy is that the angle that we come in with vertically polarized light, we optimize that so that there's no reflection on the subphase that we use, or our solution. So there's no reflection, so the camera sees nothing. But then when we put a film or something that's surface active on that surface, there's a change in refractive index, and then of course we get reflection, and then that gives us the image. So in addition to the isotherms and the microscopy, we do a lot of spectroscopy. And so we've been doing quite a lot over the last 10+ years of infrared reflection absorption spectroscopy, which really is taking FTIR, IR beam, and reflecting that off the surface, and you only get about 4%, using an MCT detector, and then doing just a very simple ratio of essentially the subphase solution in the denominator, and the numerator would be the film. By ratioing out the bulk solution and optimizing the system, we get very nice spectra of the surface film and also of ion binding, which you'll see I have quite a few slides using the infrared technique. On the bottom right, we're most well known for some frequency generation, and some frequency is a nonlinear optical tool where we bring in 2 different pulses of light. These are pulsed laser, a pulsed laser system, femtosecond, picosecond combination. And so one is we make infrared out of an OPA, and we focus that infrared beam on the sample surface, reflect off. Of course, we get transmission as well. And then the visible beam, actually from the same amplifier in this case, is about a 2 picosecond beam. The infrared's about 150 femtosecond beam. This particular system is 1 kilohertz, so a pulse every millisecond. And so these interact in time and space on that sample surface such that they generate nonlinear responses. And in this case, we capture the sum of the two frequencies. So in the sum of the two frequencies through momentum conservation comes out just a few degrees angle different because we're essentially in the plane of the paper. So in one plane, we come down, and then we capture really this sum frequency beam, the sum of the two frequencies according to this basic energy diagram, right? We've got an infrared photon energy, a visible, and the sum of the two frequencies is a little bit shorter wavelength than the incident 800 nanometer. So it's anywhere from 600 and typically I think 650 to 750 in the wavelength region that we look at. And so we capture that beam with a set of optics. It's the same wavelength that an anti-Stokes-Raman would be, and then capture it with a monochromator CCD, liquid nitrogen cooled CCD array. And there's always tricks in trying to get rid of course, the things you don't want to see in this. But the reason why we do the sum frequency over, just doing infrared is it does have some surface selectivity rules where it's just different, obviously, than the infrared. First of all, you're looking at where the overlap is on the sample, but you're also have the selection rule that you generate some frequency photons from which there's lack of inversion symmetry. So by nature, that is the air-water interface, or any interface, any change of phase would be a lack of inversion center. But also if you have structure within the interface, like an electrical double layer, that also qualifies. So your surface is not just the very top layer. It also can be several layers deep, many nanometers deep in some cases. And so that's really the challenge in some cases, is exploiting that or understanding how to interpret how much of the surface you're actually capturing. So in the neat water case, I'll talk about that in a moment. But the sum frequency is just a really strong tool, particularly for looking at, I would say, water surfaces, maybe not a surfactant covered surface, but something where we don't have a film, where we can capture it with, for example, something like the infrared. Over the last 5-6 years, maybe longer, we've been doing quite a bit of surface potential measurements. And Tessie Nadal, who's just graduating this summer, in fact, she has built and we've developed some methods of interpretation, this surface potential method that has been around for a long time, but it's not commercially available, using americium 241. And it's basically connecting the circuit and pulling out the electric field generated from that interface, such that we get information about organization that way too. Both the sum frequency and I would say the surface potential have some ambiguities in that we like to, especially with the heterodyne sum frequency, we like to interpret it in terms of dipole orientation when we look at certain signals. But in fact, the quadrupole response in both the surface potential we're learning now, as well as the sum frequency, sometimes plays a role. So this has been an interesting journey with this, and I'll show you a little bit about the surface potential throughout this as well. Please let me know if you can't hear me and if I need to put on my earbud if anything happens there.
Yeah, we can hear you fine.
Okay. Okay, so I wanted to mention a little bit more about the sum frequency generation, because I'm going to show you some heterodyne spectra because it gives a lot of information again about that orientation of water. And anyways, so the conventional sum frequency, the conventional way that one does sum frequency generation is two beams coming in, capture the sum frequency coming off of the sample. There's also a technique called phase resolve in a scanning system, or heterodyne detected in a broadband system, meaning you use a femtosecond system. And when you hear the words heterodyne or phase resolved, particularly if you're using a femtosecond system, you are taking all three of these beams after you've reflected off the surface, your infrared and your infrared and your visible. You collect your all three reflected beams, your generated sum frequency and your visible and your infrared, and you pass all three of those beams onto a local oscillator. They the local oscillator generates also a sum frequency beam, and that interferes with the sum frequency beam from the sample, and you get an interference pattern, and you're able to, in that case, do a couple inverse Fourier transforms. You're able to get the spectrum back, and we do this because it also gives you the imaginary part of the spectrum. So not only is sum frequency there's in every technique, right? There's some nuances there. So there's the real part of the index, there's the imaginary part of the index, and there's the non-resonant part of the some frequency response. So all three tend to sometimes convolute the interpretation. And so using the heterodyne in some cases has helped us understand, again, how ions might organize on the surface. And the test case for these things, Taharo and our group in the same year, but later, came up with basically the test cases where you take a positive surfactant versus a negative surfactant, and you look at the imaginary part of the index from the heterodyne some frequency, and you can actually say positive versus negative. A positive signal versus zero means hydrogens are up essentially for water molecules, so that would be the negative case. And I'll show you a little bit more there. So this is a different method and quite powerful as well. So let me just first start with water. I always like to start with water. And these are older studies, but it gives us a baseline to talk about orientation. So air-water interface. So if you look at a some frequency spectrum, Ron Shen's back in 92, 93 from Do It All. This is our spectrum, but looks the same. So essentially you get a hydrogen bonding region from 3000 approximately to 3600. Then you have the free OH or the dangling OH band at 3700 wave numbers. That is the 1 out of 4 approximately water molecules that have an OH sticking out into the gas phase. So this is what's very different about the some frequency, right? We get that signal from that dangling OH. So if you compare the surface, essentially the some frequency of a neat air-water interface to bulk measurements of Raman and infrared, both bulk, in this case, both of them are done. This was done, I think, in ATR. So with Raman, again, we get similar shape, right? In the some frequency, the infrared, a little bit different. Obviously, there's different selection rules. Infrared is change in dipole moment upon the transition. Raman is change in polarizability. Some frequency is change in both. It's a convolution of a Raman and an infrared spectrum, but with coherence built in. So there's interference effects. And also different selection rules, but there's some similarity there. And so you can actually, through the mathematics, actually compare bulk measurements to surface in this way, which is kind of nice, and I'll show you that in a moment. But just to remember that about 25–30% of the surface is straddling that surface, and the other hydrogen bonding region really captures the hydrogen bonding network. When it's in neat water, we're pretty sure, as others are, that this is really just the first 1 or 2 layers, because there's no significant amount of ions to cause any electrical double layer, and so there's really no confusion there. The confusion comes in when there's more things in the water. So that's our neat water surface, and I like to think about them dynamically dancing in that surface layer. Obviously, we need to remember that it's a very dynamic surface, and there's adsorption and desorption and gas phase 20 torr of water vapor at room temperature. So I wanted to mention that there's a lot of motivation from marine surfaces and aerosol that goes into the work that we've done over the years in my group. And oceans there's a lot of turbulence, there's a lot of wave action, it produces significant concentrations of marine aerosol. And that our world is covered by 70% plus of water. So 70% of the surface area is water. And so that's a lot of water. And that really contributes to our atmospheric chemistry and to clouds and cloud nucleation, ice nucleation in the atmosphere, and so on. And this word aerosol has gotten more attention, of course, in the last couple of years. And we all know what aerosol, I think, is now with COVID, and droplets in the air. It's not just from the ocean, but obviously continental. There's lots of aerosol as well, naturally occurring, but even aerosol from when we speak. So from the ocean, there's 2 accepted mechanisms. One is film drop, one is jet drop. Film drop is when you have the bubble essentially burst at the surface, and that film gets captured in these very small film drops. These tend to be rich in organic phase, where jet drops from the ocean, it's really the collapse of the bubble through turbulence. And these are typically larger droplets, maybe more They could be more micrometer in size, and these tend to be richer in sea salt just because of the mechanism itself is really not from the very surface layer necessarily. This is simplified, but it still captures a lot of the important mechanistic ideas. Okay, so I'm going to show you a few studies just of salts, cations, anions, just again, motivation. World's ocean is salt rich. So sodium chloride, if you think about sodium chloride and the halide series, bromide, iodide, and then also the acids of the same halides, and you look at surface tension, and you just do surface tension measurements as a function of mole fraction. Surface tension of neat water, clean water, is about 72 millinewtons per meter. That's that red line. Salts, we know, increase the surface tension of water. Acids, we know, decrease the surface tension of water. If I were to put a surfactant on this surface tension graph, it would really come down steeply, much more steeply than the acids. So surfactants, we know, really depress the surface tension of the water, and we know surfactants are surfactants. They are surface active. What's the confusion about salts is that they do the opposite with surface tension, but in fact, now there's consensus that certain ions are inherently surface active, and this is anti-intuitive to this increase in surface tension. So way back in the early 2000s, there was some publications, and then we got on this boat of trying to understand why. And so what you see here just real quickly is just from this 2004 paper, are spectra of water with salt in them. So sodium fluoride, the green is just water, the blue measurements are for the salts in water. And essentially, if I jump down here to the sodium iodide case, because that's really the most accentuated, again, the green background lower with the free OH, and then you see the red on top, which is the darkest color here, is most enhanced in this 3400 region. And so way back when, that told us that we're seeing solvation at the surface, in the surface region of these solutions at the air-water interface of a salt. So something's happening at the surface, even though this surface tension is giving us some other idea that, you know, salts or these ions should be repelled from the surface. But in fact, that's not true. So what I'm going to show you in just a couple slides, because this isn't the focus of this talk, but to set the stage, is these simplistic, very simplistic cartoons basically are the take-home messages. So if you look at something like nitrates, I seem to have missed. Oh, there it is. Okay. So something like nitrates, we do the same kind of analysis, look at these signatures, but also do the heterodyning, which tells us about direction of water. And in the end, what we are able to do is draw a picture of saying at the air-water interface, we assert from our data that nitrates, for example, are more surface active than the cations, and that's because we can see the direction of the water, water direction essentially, where hydrogens are up in this case for nitrates, and we've also looked at actually nitrate modes, but you know, comparing different salt systems. We've also done this with lots of magnesium systems, but here you see a reversal, for example, magnesium sulfate versus a magnesium nitrate, where in a magnesium nitrate, certainly the nitrate's more surface active, but turning out in a sulfate, it turns out that the sulfate is not so surface active. There's more magnesium. I'm not sure I would call it in the surface region, but closer to the surface than sulfate with certain amounts of density. And it flips the electric fields. If you have a magnesium sulfate solution versus a magnesium nitrate solution, you get opposite sign in your sum frequency measurements for heterodyning. So here we're going from 0 up here in the top right, where the positive measurements are basically the chlorides, and the negative measurements in the water stretching region are the sulfates and carbonates. And so again, this tells us about flipping of sign. All right, so let me flip back to the halide story. So if we go back to those spectra, and I said, well, initially in the early 2000s, we see a really large enhancement in this 3400, but to really know whether or not that's a surface effect or if it's just a transition moment problem, we would need to look at the Raman and the infrared of the bulk solution, of the solution phase. And sure enough, when you put salts, halides in solution and you look at them with Raman and infrared, the Raman transition moment it's really capturing something very different, right? You have less water, but yet you get bigger signals. So obviously you're getting a larger transition moment strength with fluoride, chloride, bromide, and especially iodide, which is the largest here. And nicely termed, this really is the solvation shell signature. And there's been studies since that have shown that there's nice charge transfer between the halide and the water molecules, thus giving rise to this bigger transition moment strength. So it is the water molecules surrounding that. So one says, well, okay, so is it just a transition moment strength? We're still seeing it with a surface selective spectroscopy, but it's maybe not at the very surface layer. So we need to compare the Raman and the infrared to the some frequency. And in doing something like that, one just normalizes this. And the mathematics, you can compare the Raman times the infrared to the component bands of the sum frequency in black here. And for bromide and iodide, you see a big separation. So if you look at iodide right here and normalize to 1, so this is a little bit larger than 1 for the sum frequency. For the sum frequency, it's 2.5 times larger area than the Raman times IR. So essentially what that's saying is that the interface is 2.5 times thicker for this concentration of iodide solution. So there's something going on with structure in the interface. And so if you go back to, much of my time here, I'm spending too much on this, but in the simulations by Tobias, which started this whole journey with a lot of people, in 2001, they showed an air-water interface, and they predicted that iodide would be surface active, followed by a depletion. So look at my cursor in the bottom right, and then it'd be bulk-like, and sodium would then follow. And so this prediction essentially is saying the surface activity of iodide, then depletion, followed by sodium, giving you really an electrical double layer here as well, charge separation. But because of polarizability and other reasons, iodide doesn't mind shedding its water shell to be closer to the surface. And that difference in the Z there is about for, how much more water are you capturing in a sum frequency experiment. So if you're only looking at neat water, you look at the water profile, it's only a couple angstroms. But if you're looking at change across, 8 angstroms, you're covering and you're capturing more water molecules because of that lack of inversion symmetry is larger and deeper. And so the sum frequency is capturing it's actually generating photons from more of the surface layers, many more surface layers than in water. So that's the point. Okay, so that has led us for a lot of years in thinking about surface potential too. Are there other methods to measure this electric field at the surface? Obviously, surface potential comes to mind, but there's difficulties in doing surface potential with a vibrating plate, especially on salt surfaces, but also an interpretation of that. But Tessine, again, we're just starting to publish. We've got 2 papers out, and I'll show you the next 2 slides. But essentially, we're connecting a circuit, and we're looking at the inherent field, from the air-water interface by connecting this circuit with ionization. So we need to ionize the gas in between. And when we connect that circuit, then we measure with a very sensitive voltmeter potentiostat, the surface potential or the voltage. Not technically the surface potential, so the voltage. So the surface potential itself, it needs to be broken apart into many different ways. But if we think about just comparing distance of americium versus alpha particle intensity, we know what that intensity is versus distance. So all this goes into how far away how the tool is made, what the shape of the active area of the americium, also comparison of the platinum gauze versus other like gold, for example, gives you different surface potential. So you have to take into account those parameters, and also the gas that you put in between the americium in the gas phase, whether it's just nitrogen and air, or it's argon, or it's helium. We've done all those kinds of controls. And also our control is usually looking at something like CTAB 0.3 millimolar and SDS 0.3 millimolar, because one gets opposite sign. And so that allows us to also compare to the literature. One can look at these salt solutions and look at the air-water interface by watching the measured potential as a function of time. And this decay trace has meaning. And again, through a circuit model, we can pull out with the decay trace shape we can pull out the surface tension. And that was our validation essentially for that. But where I'm getting to is what we just published some work with this instrument on halides. And if you, here again is our control in the far left, but now we look at the control SDS in the middle graph. We're looking at potential, measured potential versus, well, SDS in the first one, C-tab second, and then sodium chloride, sodium bromide, sodium iodide. And this just gives us our parameters, basically our upper limit and our lower limit, so we can normalize things to a number, to a surface charge. Sodium chloride, and what's really interesting about this, but is different than what's been shown before, is that we find that chloride and bromide actually have an opposite sign surface potential than iodide, but the trend is quite clear. And when you do this as a function of concentration, the far right is again the surface potential measured with halide concentration. You can fit these two isotherms, and you can pull out a delta G for the actual surface activity. So in all cases, even though we have opposite sign for these 1 molar sodium chloride through sodium iodide, we still get a adsorption, right? So a negative delta G for adsorption of these ions to the surface. So certainly the halides, also borne out by surface potential, show this kind of behavior. This is a whole nother talk, and talking about how one interprets this data compared to very old literature though. All right, so now I want to switch gears. I think I'm doing okay, yeah, 30 minutes. So phosphate, and I want to talk about binding at the air-water interface and some of the work that we've been doing the last few years, and really focusing on the phosphate. So this has two types of motivations. Turns out phosphate's very important in our ocean, as well as obviously we know in surface waters as well, and also phosphonic acids, which we've published on, as well as phosphate lipids, and certainly has biological importance as well. But the funding that we received, which was collaboration with AMR Flood, was really about the anthropogenic phosphate cycle, and it was through the Infuse. Actually, it was born out of a workshop, an NSF workshop, when the Infuse was highlighted. It was, I think, there was water, phosphate, and some other things that was really important. But that's where I met AMR, and that's where we initially had our discussions. But there's, phosphorus fertilizer, runoff, algal blooms, all of this are good motivation to study phosphate capture and the cycle. So the first study that we did was actually something that we started out of atmospheric, I would say, direction, because a lot of these lipids are very important in the ocean as well, and form surface active. They form parts of the surface active film, just like it's also a biologically important molecule, this DPPA. In fact, I think it's involved in neurotransmission. So DPPA is a really nice model phosphate. And so we've got lipid chain, and we've got just a beautiful phosphate group that has a couple pKa's. And we wanted to look at this model and compare and understand it in terms of binding with amino acids. So arginine was this model amino acid, and it turns out that, again, the overlap with our future work with phosphate, we're just doing it differently, right? We've got phosphate on the lipid rather than phosphate in the solution, but then we're looking at things like guanidinium and glycine and arginine, where guanidinium and glycine are part of the arginine molecule, to understand binding mechanisms and understand binding coefficients, actually. So this is the system. Arginine itself is protonated in the guanidinium group, and of course deprotonated here, so it's ion, and it has a certain K, there's a certain Ka, or excuse me, just a K in bulk solution as well, which I'll show you in a moment. And so we're looking at, though, on the surface, we're comparing bulk binding to surface binding in this case. And in the surface binding, there's lots of ways that one might pontificate how arginine could bind or may not bind at all. So our first approach is with surface pressure isotherms. And so before I talk about this, let me just quickly go to the next slide and mention, for those of you that don't do isotherms. So surface pressure, which is the surface tension difference, versus mean molecular area. And one always looks at these graphs from the right going to the left, because you spread on the surface a certain number density of surfactant or lipid, and then the barriers compress. And as you compress, you calculate the mean molecular area, but you measure the surface pressure. And so you're measuring the surface pressure, and you go through phases. So the line is just not a straight line up. It obviously has shape to it, and that shape tells you about the organization at the surface indirectly through thermodynamics. And also what I've put here to the right in these images, the black image is essentially, it thinks it's neat water, even though there's a few lipids around, because there's not enough to, there's not domains being formed in this particular case in the true gas phase. So G stands for two-dimensional gas phase, which means very far apart. So it basically doesn't see anything, but we start to see a little bit of rise in surface pressure. Let's just look at the 32 degree real quickly. That's the black line at the top. So we go from a gas to a liquid expanded to a liquid expanded, liquid condensed. So as these things start to aggregate, they many times form shapes, and these shapes are a balance of dipole-dipole forces and line tension. And so one can get very different shapes, and depending on the molecule and essentially the interactions between the head groups and the tails to then a condensed phase. So we use this technique to actually measure binding. And we took DPPA, that molecule, added arginine at different concentrations. And so the DPPA on neat water is the black trace in the far left here. And as you add arginine, essentially you expand that monolayer. So arginine is even intercalating into the monolayer itself. If you look at, arginine is made up of glycine and of guanidinium. And so the two groups are on either end. And so if you look at the glycine as a test for is the glycine causing any interaction, you don't get much change. And so that's telling us the glycine end is really not. So we take then this arginine isotherm curve on the left, and we can plot it versus concentration and actually plot the change at some surface pressure value, and we can come up with a Langmuir isotherm curve. This doesn't always work though, because if you've got if the head group and there's not a good match, and the arginine, if it was a smaller molecule, it may not actually cause a surface pressure change. But in this case, it did work. But we always then use either some frequency or infrared or both. And in this case, we use the infrared reflection, and we looked at the phosphate on that lipid, and we watched the increase of the phosphate mode, the asymmetric PO2 mode, with concentration increase of arginine. And then we compared it to our controls, the glycine, not much change, and the guanidinium, which is the other end or the control of the arginine. And we get very similar with the guanidinium, very similar result to that of the arginine. So clearly this is telling us, the three graphs, that it's the guanidinium end that is interacting. We get an increase in transition moment strength upon binding of the phosphate. Now remember, there's no phosphate in solution. This is just phosphate at the surface spread from a film. And so now here's the doing a Langmuir isotherm curve again, fitting to a Langmuir isotherm, but now we're plotting the asymmetric stretch of the phosphate instead of the expansion of the isotherm, and we can pull out the binding constants, the binding affinity. And from NMR measurements that were done in the flood lab, about a 0.1 of binding affinity, but at the surface with the infrared, we get about 7 times 10 to the 3. So about a 10,000, right? A 10 to the 4 increase, 10,000 increase in binding affinity at the surface compared to the bulk. The isotherms give us a little bit lower value, but on par with the infrared. I'd say the infrared are more reliable because, again, it's giving us that molecular probe. What's also nice about these measurements is with the Brewster angle microscopy, again, we can see what macroscopically is happening. So if we look at the bottom left, the very bottom row is, okay, so you're seeing kind of some artifacts in there. Can ignore those. There's some dust on the lens, but essentially you see a bright area in the middle, and it sort of goes out. That's the focus of the beam, so we don't have it centered. But generally, it's homogeneous. That bottom row is showing homogeneity, and this is after arginine saturation. The film becomes homogeneous no matter what the concentration after saturation. So after we reach that top of the Langmuir isotherm, but before saturation, we get these striated kind of spindles at the very surface. So very different behavior, very different structure, even though the spectroscopy and the isotherms don't tell us about this. this gives us a little bit some more interesting information, some crystallization, 2D crystallization happening at the surface, it looks like. On the top right, what you see from this study also is we looked at the CN mode on the arginine. And so the CN mode from the guanidinium end, you can see here at the bottom, and we looked in this area. And if you see in the blue graph, we're actually seeing a CN that are shown as negative bands, a CN mode here, 2 CN modes, when we have the arginine in D2O. So the top graph, the green and the black, no arginine, and you don't see that mode, right? You shouldn't, because there's no CN around. But with arginine, it's really important to say here, this is not bulk arginine. This is arginine attached to the DPPA. And the reason I know that is because we subtract out, right? It's ratioed against the bulk concentration before the DPPA is spread. So that's really a recurring theme throughout our measurements. So when you see this, it really is surface because the solution has been subtracted out very, very well. So we know that the CN is nicely, nicely attached there. And we also looked at the C double bond O. And so the C double bond O, you have 2 of them here, but really the C double bond O is a little bit different frequency on the lipid. We see some enhancement, or not enhancement, actually some change, I would say, in the C double bond O on the edge here of the C double bond O, telling us that there is some C double bond O interaction. So we think something's going on up here, maybe with this amine group. All right, so I have 3 phosphate projects I want to tell you about, and I think I'm doing okay in time in the pretty short slide. So phosphate project number 2, now we're taking the phosphate, we're taking it off of the lipid, and now we're saying, okay, we've got phosphate in solution. Now in the Flood lab, they designed receptors, some of them guanidinium based, to test and to see what, number 1, what would be the binding affinity, and what would be the mechanism of that binding, and would there be any enhancement at the interface because of the interface itself, as opposed to bulk. So these are the 4 molecules that were made. So all of them obviously are surfactants. So the first 2, so the urothiourea on the left, no charge, 0 charge, and this is our symbol for it, so 0 charge. The U, just meaning 2 chain, euthioureonium, which has a charge and also a methyl group on this thiourea group. So it's shown as a positive charge here with a little extra chain there. So it's kind of almost got 3 chains. The euguanidinium, again, 2 chains with a positively charged guanidinium, symboled as this. And then S, meaning single chain, guanidinium, positive charge. All right, so we look at all 4 of these with isotherms and with phosphate. So the black or the gray underneath you see is the isotherm without phosphate in solution. So just of the receptor or the surfactant. And then when we add phosphate, then that's the shaded area that you see over that. So S-guan, U-guan, you really don't see any difference, nor do you see a difference with the euthio. So this was the one with no charge. But the thioureonium, positively charged, you'd get very significant change. Let me point out here in the guanidinium, there's a slight expansion, very slight expansion with the euguanidinium, but it's really the euthioureonium that gives us the biggest response and biggest change with the isotherms. Okay, story's not over because we need to look at the spectroscopy to know whether or not this is really valid. Well, in the spectroscopy, let me just cut to the chase. The S-guan and the euthioureonium, no change. The U-guan does have a change, even though it didn't show, really, it showed relatively little change. It was still within the error of the isotherm. It shows significant phosphate binding. So you see here in the phosphate bands in red here with circles around them that I'm circling myself. You see huge enhancement. The black, there was no band there before. There was no, it was on water. And this is the phosphate where again, yeah, so on water, and then but then we ratio out the solution. So the red spectrum is a totally different set of spectra. It's the solution as a background, and then the spread film on the surface. And so we're only seeing the phosphate that is bound. The thiuronium, we also see change in this region, but certainly not like the euguanidinium, even though the euguanidinium did not give us much response in the isotherms. We also did in this paper, in this work, competitive studies with the phosphate versus the chloride, and know at what point do we actually get diminishing returns on the phosphate, and that there is some diminishing returns, but there is selectivity. There still is high selectivity. So in looking at the IRRAS, it was most reliable, the infrared reflection absorption spectroscopy, and plotting those as a concentration of phosphate, we get a binding constant of about 10 to the 5 per mole. This experiment on the bottom right is when we have a constant 1 millimolar sodium chloride background, again, still showing selectivity of the phosphate, but very different shape curve clearly here. But notice we've got a logarithmic scale on the bottom. So the euguan receptor shows selectivity towards phosphate up to about 1,000. And the euguanidinium binds to the phosphate with this K of 10 to the 5 with a 1 millimolar sodium chloride background. So these are those final experiments on the top right, which show that selectivity of the 1,000 is the cutoff point, 1,000 to 1. Okay, project number 3. Now this one's not yet published, but we're really close. And we've actually have more publications together, but this I think is maybe your second to the last one that's going to come out. So it's a very productive collaboration. This molecule, cyanosurf, I think AMAR has published, I don't know, at least 10, 20 papers over the last 10 years on this molecule here. But when we collaborated, it's all about the air-water interface. It's about making something a surfactant and seeing if that surface environment changes things. And then we know it will in some way. Will it enhance something? Will it not? This molecule itself, the cyanostar macrocycle, is hugely greasy, right? Hugely hydrophobic. We're putting more hydrophobicity there. It's neutral charge. So it's not a surfactant. It's just a big greasy thing, essentially, at this point. And so, but just as a backdrop, if we talk about UV-Vis and NMR and binding and looking just at cyanosurf itself, or actually this was with the whole molecule, what we call cyanosurf instead of cyanostar. AMAR's lab also did binding constants there. I'm not going to talk about this, but I'll show the comparison at the end. So, all right. So will cyanosurf bind to the same ions that the cyanostar bound to in the bulk organic phase? And so those ions that have been tested are phosphate, of course, H2PO4. So when I say phosphate in solution, it's always H2PO4 with a single A- charged. That's the predominant species of the pH that we're working at. The hexafluorophosphate, PF6-, perchlorate, and chloride. So in solution, cyanostar binds PF6 approximately to that of the perchlorate at a 2 to 1 ratio. The chloride is next, but about 4 orders of magnitude lower in binding constant. So phosphate, according to AMAR, is a lot more complicated and binds certainly with different stoichiometries in bulk solution of bulk organic solution. But he asserts that it's on par with the PF6 and the perchlorate in some ways. So it's really difficult to say what's the strongest binder, I guess, in the organic solution. So let's see what happens at the surface. So this is the idea. Cyanosurf, very hydrophobic. You bring in an anion that cyanostar wants to bind, even though it's not organized at the surface, and poof, okay, it binds. Then all of a sudden this becomes a surfactant molecule. And then we should get, the prediction is, we go from something that might be disorganized to something that's very organized, like a very nice surfactant, and we get something that looks like an isotherm, and then we have spectral evidence for that. So that's the hypothesis. And this is what we get. All right, so cyanosurf spread, let's just talk about the first isotherm and the black curve here on the top left. So we're looking at surface pressure again versus mean molecular area. We read from right to left. And so as we spread a small amount of the cyanosurf on water in black, we don't see anything happen until about 80 angstroms squared. It actually has an isotherm, which is surprising. I thought it was not going to show anything. So even though it's extremely hydrophobic, it somehow acts somewhat like a surfactant totally surprising, and I don't understand that yet. When we place the cyanosurf and do the spread on a solution, a 10 millimolar solution of the hexafluoride, we certainly get huge expansion across the whole region. And the collapse phase is a little bit sooner at lower surface pressure. Similarly, perchlorate acts the same way, a little bit different shape, but very similar in shape. Okay, so these two ions, really we see evidence, strong evidence of binding and changing of phases. But then you go to H2PO4, the phosphate and the chloride, and again, really nothing. It's on top of the isotherm of water, little bit of change with the chloride. There's actually a compression, a decrease in surface area, saying that the chloride is acting to really bring the cyanostar head groups closer together, but very small. All right, so we don't want this. We want this made sense when I put it together. I'm not sure it made sense right now, but we want cyanosurf to be on the water, not in some other phase. So what does it look like when we do the Brewster angle microscopy? If we look, what I have here is at the top, it is aggregated with ions. So you see really a mess, right? Lots of white, lots of big aggregates at the surface. This is just on water. And so even though cyanosurf has an isotherm, and there is some spread, it's really messy. So at large amine molecular area, there are definitely big islands of aggregates throughout the whole thing. On H2PO4, even though again, we did not see any interaction with the isotherm, lots of aggregates. So, okay, that makes sense. It looks just like it does on water. The chloride, I need to go out and look more at these images, but very, very similar again. So all of them really not doing anything, really not binding significantly, certainly. But we do know from the isotherms, the perchlorate and the fluoride, the PF6, become homogeneous. And that makes sense that they're completely different than the aggregation and the monolayers that were not binding. So when it binds, it forms something that's very homogeneous and 2D film-like. I'm going to pass. So there's lots of different scenarios that we're trying to go through in our head of what the binding might be. So then we look at the spectroscopy, the infrared again. What am I doing? I'm going too slow. So bottom line is, like I showed before, when we see an intensity, these are negative intensities at the place here. This is the CLO band. Over here on the top right, this is the PF band. Again, big enhancement. Again, we're ratioing out the bulk solution. The perchlorate and the PF6 in the CH2 region is also changed from on water. And we actually see shifts, which are telling us that there's actually more disorganization of the chains. So we believe that the perchlorate and the PF6 are intercalating in there, and they're actually spreading the cyanostar further apart, and the chains then have more room to have more gauche defects. And so that's what the blue shift is about. So definitely significance. So with the sum frequency, what's really nice about the sum frequency, when you look at the water region, it's its own tool in itself, because the water tells you a lot about what's going on with the surfactant and the ions. And so if you look at the top left, this is without the surfactant, no surfactant on it, but this is just the ions, and these are all separated, layered on top of each other, just so you can see them. They all look the same. They all look the same. So because this is such a small 10 millimolar, you don't see much surface change in the water structure. But if you then spread the cyanosurf on, and remember, we start with a neutral molecule, and when it binds, it becomes negative. If it becomes negative, all of a sudden you get enhancement, because now your probe depth is larger because you have a negative, negative surface charge, and you've got water ordering below it. And so it changes that lack of inversion. There's lack of inversion deeper into the solution. So the PF6 and the perchlorate, the one that we know binds strongly from all the other data, gives us huge signal enhancements consistent with that binding and causing the neutral molecule to become charged. And the other ions and the water, again, are on top of each other at the bottom. So these are not stepped up versus the left side. So beautiful turn on, binary kind of signature for that. We've also done other work that's published where we've also used the sum frequency region. In this case, we weren't making a charged surface. Here we were actually quenching the water region, and we were looking at, this is the U-guanidinium from the second study I talked about. And so guanidinium itself is charged, and so it gives you a huge enhancement in the sum frequency. And as you add binders, the better the binder, actually, the bigger the decrease in the water region, because again, you're quenching that charge. You're making something, in this case, go from charged to uncharged. Where in the cynosturf, we're doing the opposite. So the water region, again, is the telltale sign of charge at the surface caused from either binding or not. So clearly for the cyanostar, the PF6 and the perchlorate were the winners, and very, very strong charging. So, and I don't have the data on the binding on these yet. I think we just decided to do the perchlorate. That's leeway. Okay, so I discussed a lot. I have one more slide after this. I have one more slide, but I did show you a lot about air, water, showed you a lot about maybe lipids and organics receptors at the surface and binding. And just lastly, especially I talked to Pan-Sun and Mark right before this talk. They have some beautiful data, but Liwei's only in my group for 2 more weeks. She's going on to a job after this. But we started to look at this molecule that I think a lot of you know much better than me, this DEHPA. And we looked at pH 6 versus pH 2 with isotherms in cerium chloride. And I think, like Mark and his students know already, you're going to get changes in this region. And at pH 6, you're deprotonated. So this molecule is very soluble in water. And so the red line is essentially saying when we do an isotherm, there's nothing there, it just goes into solution. So we're doing it a little bit different than you were, of course, Mark. We're doing it like an isotherm. We're saying, oh, let's just pretend it's surface active. We're going to spread it like a surface active molecule and then see what happens, and if we can get an isotherm. And it does act like as a surfactant, surface surfactant, not soluble even at pH 6 when you add the 20 and the 2 millimolar cerium there, and you get really a nice phase change through there. And you can see in the top, very top, with the same solutions, the black is on water, and with DEHPA, with the cerium, you get huge phosphate band. Again, telltale sign that the phosphate is binding to the cerium. And we've done other work on that. So that's it. And this is, well, the most in-person group pictures. This is a couple years old now, but again, funding and all my students. And I appreciate your time and hope I have a couple questions. Thanks very much.